All right, so in this video, I'm just going to show you how to do these two problems that you were supposed to attempt. If you feel very comfortable doing these types of problems on your own, you can choose to skip this video if you'd like. So we were supposed to find the output as x gets closer to 1 of the function g of x. And then we were supposed to find the output as x gets closer to pi of the function sine of x. Let's do this first numerically. And I'll take on one function at a time. So I'm not going to deal with the sine of x until we complete the g of x equals 3x minus 7. In the last video, when I inserted my table, I basically went and I did two tables. You don't always have to do that. If you'd rather, you can do this all in one big table. It really doesn't matter. But we do need to approach the number 1 here. Go 1 right here. From underneath. So maybe start at 0.9 and then 0.99 and then 0.999. And then also from above. So 1.001. I'm trying to get closer to 1, so it looks like that, as I start from from down further in the table, and I approach 1 as I travel up, and as I start at the top of the table, I approach 1 as I travel down. So if I plug in 0.9, I end up with an output of my function. I'm sorry, this function is called g, not f. My output becomes negative 4.3. If I plug in 0.99, my output becomes negative 4.03. And if I plug in 0.999, my output becomes negative 4.003. And if you didn't see a pattern in the outputs, then you might want to go further. I hope that makes sense of what I'm saying there. If you ever don't see a pattern yet, you can always say, well, let's get a little bit closer. Let's take another x value and plug that in. The nice thing about doing this on a computer is that you can insert another line to a table anytime you want. So as x value gets closer and closer to 1, we try to look at the outputs and see what values are my outputs getting closer to. Now let's do this from the other side as well. So I'm going to start down at the bottom, insert 1.1 into g of x, and we get a negative 3.7. If I insert 1.01, I get a negative 3.97. And then if I insert 1.001, I get negative 3.997. Now, I didn't mention this before, but as you can see, our x values are getting closer. And typically the way I do it is I start with being like a 1/10 off of what the actual value is, and then I get closer by factors of 100. So I get like a 1/10 off, 100th away, 1,000th away. And if I need to, maybe I insert another line and I get a 10,000th away. This is a 10,000th away from underneath. This is a 1,000th away from underneath, 100th away from underneath, 10th away from underneath. So that's the way I typically do it, but there's no reason that you have to do it the way I do it. You could get closer, by halves if you wanted to. But as I look at this from underneath and from above, it looks like my value of 1 keeps getting closer and closer and closer to -4. And that does happen to be what you get when you plug in a 1 into G, right? So as you came in from underneath, you got closer to -4. As you came in from above, we got closer to -4. And that just happened to be what you get when you plugged in that. So what we would say is we would say as x gets closer to 1, the function g of x gets closer to -4. All right. And we can look at that through Desmos by just graphing g of x equals 3x minus 7. I'll just graphed it in the color black. Again, I'm just on desmos.com/calculator. And so in this case, we want our x value to get closer and closer to 1. So I look at my function. I'm going to try to draw my cursor here right at 1 and right and get closer and closer to 1. So here's my cursor getting closer and closer to an x value of 1 as I travel along the line. And as I travel along the line, it looks like it's approaching this point here. So where the x value is 1, and obviously the y value is -4. If I go from underneath, as I get closer and closer to an x value of 1, it looks like I'm going towards that point again, that point being 1, -4. So again, graphically, it confirms what we can see numerically. So these should always match up. If they don't match up graphically and numerically, then something is off. All right, so let's take the next example, the sine of x. So as x gets closer and closer and closer to pi. Now we're going to have to be a little bit careful here about how we set up our table. How do we get closer and closer and closer to pi? Is approximately 3.14159, etc., etc. How far do we want to go out? 2, 6, 5, 4, dot, 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 right? So that's a rounded number, but you can see where it's going. So if I want to get closer to pi, maybe I start at 3.14 from underneath, then go to, I don't know, 3.141. That's what I'm doing here is I'm rounding to 2 decimals. I'm taking what's called the floor. So I'm going to 3 decimals, and then I am going rounding down. So let me explain by doing the opposite side. This will make more sense. 3.15. So if I go to 2 decimals, I'm going 3.14 and 3.15. You see that? This is called the floor and the ceiling. This is always rounding up, always rounding down, no matter what number is afterwards. So if I go to 3 decimals and I pretend that there's no number afterwards, we get 3.141. That's what we get when we round down. Again, 3.142 would be what we get when we round up at 3 decimals. So we go out to 4 decimals, 3.1415 if I'm forced to round down, 3.1416 if I'm forced to round up. All right, so that's one approach to do it if you're getting closer to a number, which is like irrational, you can always do that trick as well. So again, I'm trying to give you a few different tricks to be able to approach a number, right? We approach it, I get a tenth, a hundredth, thousandth, 10,000th, just keep getting closer to it. Or if it's an irrational number, you can just do that trick. You round to 2 decimal places, make sure one side is rounded down, the other side is rounded up. All right, again, that's not correct rounding on both the sides, but you force it to be. So we take sine of x, and now we're going to plug in those numbers. If I plug in 3.41, whoops, excuse me, 3. Did I say 41? I meant 14. Keep saying bad things today. I end up with 0.00159265. That's what my calculator gives me. Okay, that might be a slightly rounded number. If I do 3.141, n is my x value, technically, this is 5 times. On my calculator, I get scientific notation is what I'm trying to get at. So I get 5.93 times 10 to the -4th, which is a really, really small number, right? For those of you who don't know, scientific notation, that'd be 1, 2, 3, 5, 9, 3. There we go. We'd have to move that decimal point over 4 spots. If you go 3.1415, that's even a smaller number, 9.27 times 10 to the -5th. And that is like 0.3, another 4, and then 9. Again, I'm just kind of rounding these things, but that's the idea. So you can see you got nearly 0, and then this got even closer to 0, and then this got even closer to 0, right? Let's do the other side. I'll start here at 3.15. I got a negative 0.0084072. That's what my calculator gave me. If I do 3.142, I get a negative 4.07 times 10 to the -4th, which is negative 0.000407. Okay. And then when I type in 3.1416 into the function, my calculator gives me negative 7.35 times 10 to the -6th. Again, that's negative 0.1345, and then 7.35. Okay. Hopefully that makes all good amount of sense. I don't know how I'm getting those numbers. So question is, what is this getting closer to? So as we get here, notice these numbers are getting smaller and smaller and smaller in terms of absolute value. They're looking like they're getting smaller and smaller and smaller. This is getting closer and closer to 0 on the negative side. This is getting closer and closer to 0 on the positive side. So it looks like as x gets closer to pi, the function h of x, or the function's output h of x, gets closer to 0. All right, so that's the idea. So as x gets closer to pi, h of x gets closer to 0. So h of x equals sine of x. Graphically, if we can graph this, if you can find where pi is at, right? You take a point on this graph and you find where pi is at. It looks like, yeah, as that point gets closer and closer, or excuse me, as the graph gets closer and closer to pi, from the left, it looks like it is getting closer to 0, or the x-axis. And from the right, as we approach this way, it looks like it's going towards the x-axis. Now, this is harder to see because of the nature of pi, 3.14. Sometimes you can mess with the settings on your calculator or on Desmos to, highlight pi and 2 pi. But right now, this kind of looks hard to see graphically. Not that it's, once you see it's hitting 0, yeah, it's hitting 0, but, where is pi? It's hard to identify pi on a graph on the x-axis unless you know something prior to. So that's how we figure things out, both numerically and graphically with this example.